In this activity, we're going to take a look at what's called angular sizes. So first off, why does this matter and what is it? So the angular size of an object corresponds to how big it seems in your view. So essentially, if we see something as small, that doesn't necessarily mean it's actually small. It could mean that it's far away. So just because something takes up a certain amount of your view that your eyes can see doesn't mean that it's big or small. Distance is going to play a role in this as well. Just like I can hold my hand up to my face here, it can block a large amount of my point of view. If I move it further away from myself, it blocks a smaller percentage of my point of view. Now, the size of my hand isn't changing, physical size, but what I am changing is its angular size. Up close, it's taking up a wide percentage of what my eyes can see, so that's a large angular size. But the further away I move it, the smaller the angular size. So angular size is something that's the easiest for astronomers to go through and measure because it's just how much of our view is something taking up. It's not until we're able to add distance to be able to figure out actually how physically large things are. So if we take a look at what we could see, say, in the night sky, unless we know distance, we have no way of knowing which is bigger, the sun, the moon, Jupiter. We could just see how much they take up in our sky. So you'll actually go through and investigate how much space the moon and the sun take up out of our whole sky. I'll tell you that they're both larger than Jupiter, but once we take distance into account, we can tell that Jupiter is actually physically much larger than the moon. But you need to know both. You need to know the angular size as well as the distance in order to figure out physical size. So when we talk about angular size, we actually can measure this amount. The full sky all around Earth is 360 degrees, so one full circle. And this picture is very much not to scale. This is for illustrative purposes only. But when people say they pulled a 180, that means they turned around. If someone does a 360, that means they turned all the way around to end up facing back where they started. So there's 360 degrees in one circle. If we take one of those degrees, which is definitely not as big as what's shown here, but imagine that we take one and we divide it into 60 equal parts. Then what we have is called an arc minute. And so this apostrophe, this slash, represents an arc minute. So there are 60 arc minutes, that's ARCMIN, in 1 degree. Just like there are 60 minutes in an hour. Now if I take one of those arc minutes and divide it up into 60 tiny pieces, then I've got what's called an arc second. And arc seconds are defined by the 2 dashes there. So astronomers actually don't like using the apostrophes for feet and inches because we use them for arc minutes and arc seconds. And again, just like there are 60 seconds in a minute, there are 60 arc seconds in an arc minute. So we're going to use these measurements to describe how much space something takes up in your view. Basically what we mean when we talk about angular size. So let's take a look at what this will look like for your lab and what specifically you'll need to go through and do to get ready and do this particular activity. Before you start doing anything in the lab, you want to take the page on the back part of the packet, hold it out at arm's length. If you have a tablet or computer screen, just make sure the screen is at arm's length from you and make sure that it's actual size. Holding it out at arm's length with your arm nice and straight and elongated there, you're going to make a prediction as to how big you think the sun and how big you think the moon is in the sky compared to those circles. So this prediction is for you. You'll mark inside or next to that circle which one you think best closely represents the size of the sun and which one most closely represents the size of the moon. Once you do this, you can go through and start the main part of the lab. In order to calculate angular size, we need to know both the diameter of an object and the distance to that object. These two need to be in the exact same units. Then we multiply by 57.3 degrees. Let's take a look at an example that involves a soccer ball. The diameter of a normal soccer ball is about 9 inches. So let's imagine that we want to figure out the angular size of a soccer ball when it's at two different locations. Distance number 1 will be when it's only about 5 feet away from you. Distance number 2 will be when it's 50 feet away from you. So we'll go through and calculate the angular size of that soccer ball at both of those distances away from you. That way you can get an idea of how angular size changes for different distances. So for distance number 1, we first need to go through and convert it to the same units as our soccer ball. Since our soccer ball is 9 inches across, we want to go through and calculate our distance in inches. So we're going to convert our 5 feet into inches using our method from before, and that gives us 60 inches. We'll do the same for 50 feet. Since our conversion is 1 foot for 12 inches, we can see that that turns into 600 inches. So our diameter of our soccer ball is 9 inches, divided by the distance away, which is 60 inches, times 57.3 degrees. The inches cancels, so we have 9 divided by 60, which is 0.15, times 57.3 degrees, which gives us a final angular size of 8.6 degrees. We'll repeat this process for the second distance, 50 feet. So again, we're still dealing with a 9-inch diameter ball, but now it's at a distance of 600 inches. 9 divided by 600 gives us 0.015, and that's then multiplied by the 57.3 degrees. Once we multiply those final two numbers together, we'll find that the angular size of our soccer ball at 50 feet is only 0.9 degrees, or less than 1. First, we want to tape our pictures up on the wall, roughly at eye level height. My eldest here is going to be our model. So first we'll go through and focus on the fist. So go ahead and stick your hand up with your arm straight out, and you want to close one eye, and you're going to walk backwards until your fist fills up that whole circle. Do you think that's good now, Elliot? Mm-hmm. Okay, let's check. So if we pretend that we are his eyeballs and try and get away from his giant hair. I'm glad you think this is funny. Alright, we're just gonna get in front of your face. Then the basic idea, stop moving your arm. The basic idea is that you want your fist from knuckle to knuckle to be exactly in front of, wide as that circle. So based on where the camera is right now, would you stop moving your hand?
It's hard.
You don't have to look at the camera. So based on where he is right now, the camera's showing it's a little bit bigger, in fact. Step a tiny bit closer, Elliot. Something closer to that. But he's messing up because he really wants to see the video. But that's roughly the idea. Let's see. All right, I'm gonna do me then, because I can't make you hold still. So something like that. So that would be a fist. And then you're gonna do the same thing for the other one. This one says pinky, so we wanna do it with our pinky. Same idea, we wanna get ourselves close enough so we're just barely covering that up, like that. Once you've gone through and calculated the angular size of your fist, thumb, and pinky from the pictures, the next step is to go through and figure out what the angular size of a door is. Most doors are standard size. So you want to make sure that you're 5 feet away to start, measure that the best way you can, and then you're going to use some combination, whatever you need, of your fist, thumb, and pinky to be able to work yourself across the door all the way. So if you look at what Elliot's doing, he's sort of working his way over until he gets all the way across in his eyesight. Again, sort of keep your eyes closed, one eye closed, until you can go through and measure however many you need. So 4, 5, 6, 8 fists, whatever combination you happen to need. Then you'll repeat this again at the back of whatever room that you're at, knowing that everyone's rooms are going to be a different distance. Say hi, Elliot.
Hello.
Thank you for your help.